talk about surface area, let's just review some area formulas for various shapes that you would have seen. We've already talked, I believe, a little bit about rectangles because you would have done some of that in the unit conversion stuff. But some area formulas that are important to know. And this is by no means an exhaustive list, but it's some of the ones that will come up frequently, is firstly the rectangle. And the area of this is length times width. Okay, there's a square, which is just a rectangle with 4 equal sides. So I'm just going to call this x, this side length. And so if it's length times width, it would be x times x, right? So the area here is x squared. Okay, there's a triangle. Do you guys know what the area is for a triangle? Yep. That's circle. Circle, what did you say, Gideon? Yeah, base times height over 2. And the reason for that is that a triangle is kind of like half a rectangle. So triangle, this is the base. The height is always perpendicular to it. And so the area is base times height over 2. And the reason is that if we filled this in, and made it into a rectangle, this would have an area of base times height, but we're only taking half of this and half of this. So that's why it's base times height divided by 2. Okay, and then finally I want to talk about a circle. And that was the one that you just mentioned, which was pi r squared. Okay. There's another important formula when we talk about circles, which is the circumference of a circle. So I'm going to write that down as well. And circumference is like the distance around the outside, right? It's kind of like the perimeter equivalent. So circumference is either 2 pi r or pi d, pi times diameter. All right? Okay, so those are some common area formulas. What is the surface area? What does that refer to? What does surface area mean? Yeah.
The surface area of the whole, of like a 3D shape?
Yeah, so if we look at it, it always refers to 3-dimensional shapes. Okay, so, and if we're trying to find the surface area of this, let's say, what would we be looking for? Yeah.
The area of each side, I guess you could say.
Uh-huh.
Can you multiply that by 6? Because
Okay, so for a cube, yes, but in general, we look at the area of each side, and then what do we do to all those areas? Add them, yeah. So the surface area is the sum of the area of each face of a 3-dimensional object. Okay, so in grade 9, what you look at is surface area of prisms and cylinders. And those can kind of go together into one category because prisms and cylinders are all tubular. And what I mean by that is that if you look at the two ends and you take them out, you'd get a tube on the inside. And if you take a cross section of the tube, you'd see that base. Okay, so this is tubular, two ends are exactly the same. This is tubular, right? Two ends are the same. And we call that the base. The base is not necessarily what the shape is lying on. If I set this up like this, okay, the base is not, for this guy, a rectangle. The base is a hexagon because the base always refers to the two ends that are the same. Okay? And prisms, which are tubular, are named after their bases. So this is called a hexagonal prism. And this guy is called a rectangular prism. Okay, so last year you looked at surface area of prisms. Okay, so you could have like a rectangular prism. Okay, a triangular prism, I always think of a Toblerone box. This is rectangular. A triangular prism looks like that. And again, the bases of these things are the triangles. It doesn't matter that I've drawn it so that it's lying on one of the rectangular faces. This is called a triangular prism. You can have like the Pentagon in the United States. Have you heard of that building? Yeah, that's a pentagonal prism. If you look at the sort of bird's eye view. Oh, that's a terrible drawing. What am I doing here? Anyway, that's a pentagonal prism. And you can have octagonal prisms, hexagonal prisms. A prism that's like a circle has a special name. What is this thing called? Cylinder, that's right. So a circular one is called a cylinder. Why can't I spell today? Cylinder. Okay, and then this can kind of be categorized in the same way as other prisms. The volume formulas for cylinders versus prisms are identical. Surface area is going to be a little bit different. Okay, so what I really want to review today is this one and this one. Okay, and then we'll start talking about adding in some more shapes. And essentially, all we're going to do with surface area and volume is take what you've learned last year and add in some extra shapes. And the different types of extra shapes that we're going to add in are pyramids, something that looks like this or like this. Those are both pyramids. We'll also add in the cone, which is kind of like the pyramid version with a circular base, and then also a sphere, which is a ball-shaped. Okay, but that's really all that we're going to do. And then the other thing that we could do actually is I could do something like this, where I take this guy, this is a cylinder, and this is a rectangular prism, and I stick them together. And that's going to sort of change the surface area formulas a little bit, because when you stick two shapes together, certain surfaces get covered up. So not all of the surfaces are exposed anymore. Okay, so we'll look at that as well. And you hopefully would have looked at that a little bit last year as well. Okay, so let's start with the rectangular prism. So if I take this guy and I unfold it, that's called a net diagram, or a net of the 3D shape. And so what I would end up with, and by the way, these have 3 dimensions. So I should maybe say that first. This is a length, a width, and a height. Okay, and if I unravel this, I will essentially have this kind of thing going on. Right, so this is the front and the back, and this is the top and the bottom, and then I've got these 2 sides coming out. Okay, and I have one, I mean, there's little flaps on this one, so it's not perfect, but I cut open a box of chalk so you can kind of see what I'm looking at, okay? Now, if we put some of these dimensions in here, this guy over here is the width, and this is the height. And these two are identical because these are the two ends, right? So this is also the width and the height. And then along here, we've got the width and the length. This is also the width and the length. And then this is the height and the length. Okay, so we're looking at adding up 6 rectangles, but some of them are the same. Okay, so we've got, this guy would be width times height. This is also width times height in terms of its area, because you multiply the two sides together, right? This is length times height. And this is also length times height. And then these guys are length times width and length times width. So all together, there's 6 faces, but they come in pairs. So I've got 2 length times widths, 2 length times heights, and 2 width times heights. And that's the surface area of a rectangular prism. Now, you guys have probably seen this before. If you haven't, that's okay. But the reason why it's important to pick this apart a little bit and really have an understanding of, for this formula, what do these various terms mean, right? The 2 length times width, that's really talking about 2 surfaces, and it's the bottom and the top of the rectangular prism, right? That kind of thing. The reason why being able to understand that is important is if I asked you for the surface area, let's say, of a skyscraper, the skyscraper is cemented to the ground. You can't lift that up. And so you would actually have to take out one of the surfaces. So you have to know how to manipulate this formula to suit the problem that you're solving. Does that make sense? Yeah? Okay, cool. So there's your rectangular prism. This is on your formula sheet. You don't need to memorize it, but you do need to understand where all of the pieces are coming from. And then the other one that I want to look at is the cylinder. Okay, now if I were to unravel a cylinder, then we can see that the 2 ends are circles. So I've got one circle here, one circle here. If I undo the tube part, that actually makes a rectangle, right? This is what it looked like. It's like having like the label to a can. If you unravel it, it makes a rectangle, okay? So if I make a net of the cylinder, and a cylinder also, I should mention, has 2 dimensions. It has a radius, or it's not really 2 dimensions, it's 3-dimensional, but it has 2 defining lengths. One of them is the radius, and the other one is the height of the prism, or cylinder, I should say. So if I unravel this, I'm going to have 2 circles. I have to make this a little bit. For the 2 ends. And then in between, I've got this rectangle. Okay, so this is the radius, this is the radius. This height over here becomes this piece of that rectangle. This is the height. Okay, so for the circle, I mean, we know these are pi r squared, and this is also pi r squared. Here we've got a height here, and then this guy. Where does that come from? What part of the circle is that? Yeah, it's the circumference of the circle, right? So this length of that rectangle is actually the circumference of the circle, which is 2 pi r. So the area of this rectangle is length times width, 2 pi r times h. Okay, now when we put this all together, I've got two circles, which are 2 pi r squared, plus this rectangle in the middle, which is 2 pi r h. Okay, again, you do not need to memorize this, but you do need to know that the 2 pi r squared refers to the two ends, and the 2 pi r h is like the tubular middle part. Okay, this is all on your formula sheet. Okay, so if you look at your formula sheet, you will see all of these surface areas. There's also something on your formula sheet, some of you guys have it out. You'll see surface area, for example, equals 2 length times width plus 2 length times height plus 2 width times height. And then you have something called LA. LA stands for lateral area. And the lateral area is where you take off the bases. So if you're talking about a cylinder, you would take out the 2 circles. If you're talking about a rectangular prism, you would take out the 2 length times widths. And you're just looking at like it's almost like a hollow tube. Okay? When you're talking about a pyramid, right, I would take out this part. Or if I was looking at this one, these are kind of hard to undo, but you would just take out, oh my gosh. Let's see if I can do it. I should have brought my magnetic ones in. Those ones are better. I'm going to have to use something here to pry this open. Come on. I'm going to break my smartboard pen. Let's see. Nobody in this class plays with these blocks. In my other classes, people play with them, and then they could help me out with this. Oh my gosh. There we go. I got it. Okay. So that would be the lateral area of this pyramid. You'd take the base out. Okay. Questions with that so far? All right. So we are going to move on to these new shapes. Surface area. And as I said, in Math 10C, all we do is add some additional 3-dimensional objects. And the ones that we're going to add are the pyramid, the cone, which is kind of like a circular pyramid, and a sphere. Okay, so let's talk about a pyramid. A right pyramid is a 3D object that has triangular faces and a base that's a polygon. So these guys are actually named after their polygonal bases. So this guy would be a square pyramid. Okay. The shape of the base determines the name, so we just talked about that. And then basically one end is a polygon, the other end is a point. And so basically you have triangles that come up to that point, and that point is called the apex of the pyramid. Okay? The height of the pyramid is the distance from the apex to the base, and it's usually right through the middle of the pyramid. Okay, so it's not something that you would see on the outside. And it's perpendicular, of course, because perpendicular means it's the shortest distance from that apex to the base. Okay, so this is called a square pyramid. You could have a rectangular pyramid. And my trick for drawing these is I draw the base like that. And then I draw a point. And then you just connect the 4 corners up to that point. Okay, so this is a rectangular pyramid. Sometimes you'll see the roof of a house might look like that. Okay, you can have other ones though. You can have like a pentagonal pyramid, or let's do a hexagonal pyramid. So there's a hexagon. Okay, hexagonal. You can have a triangular pyramid. I don't know how I forgot that one. And then a cone is not a pyramid, but it's kind of the circular equivalent. Okay? Now, one thing that I also want to mention in a pyramid is something called the slantite. And the slantite is basically the height of one of these triangles. It's like the slanted height. You can see why it's called the slanted, because it's going to be slanted to get up to the apex. This over here is the slant height. And depending on the type of pyramid, you may have more than one slant height. If you're talking about a square pyramid, all of the triangular faces are going to be identical because all of the bases are the same. But if you're talking about a rectangular pyramid, you actually have two different triangles there. And so you might have two slant heights. Okay? The other thing I want to talk about is something called a tetrahedron. And that's the one I just took apart. This is a tetrahedron. It's like the triangular equivalent of a cube, right? A cube is a shape where all faces are the same and the faces are all squares. So this is a cube. Okay? A tetrahedron is a shape where the faces are all triangles. And a tetrahedron is a type of pyramid. It's a triangular pyramid, and it has four faces. There's the triangular base and then three triangular sort of slanted things that go up to the apex. Okay? So you will see that word and you need to know what it means. The nice thing about a tetrahedron is just like a cube, all faces are the same. So if you can figure out the area of one face, you just multiply it by 4 and you get the surface area of the whole thing. Right? Just like with the cube, you find the area of one square and you can multiply it by 6. Okay, so over here we have just pictures with the slant height. And then the surface area of a pyramid is going to be the area of the base plus the area of all the triangles. Okay? So let's try a couple of examples. Okay, so here's the first one. Ooh. Jean-Marie measured, then recorded the lengths of the edges and slant height of this regular tetrahedron. What is its surface area to the nearest square centimeter, and what is the lateral area? Okay, so if we know that it's a regular tetrahedron, that means all faces are equal, which is nice. So if we're trying to find the area, the surface area of this thing, well, if we're looking at the surface area, how many faces do we need to calculate? Yep, 4, yeah. So the surface area is going to be 4 triangles. What about the lateral area? Yep, 3 triangles, exactly, because you just take out the base. The lateral area is 3 triangles. And I will often set up my work like this, where I'm breaking the surface area down into different faces and what their shapes are. So here, if I'm looking at 4 triangles, it's 4 base times height divided by 2's, right? So the base is, let's see, the base is 9, and the height of the triangle, which is, what part of the pyramid is the height of the triangle, by the way? What is this called in the context of the pyramid? Yep. It's not the height, almost. It's the slant height, yeah. The height goes from here. Yeah, this is the slant height. That's important. We're going to do more on that later, okay? But it is also the height, rather, of one of the triangular faces. So this is 4 times base times height, 9 times 7.8 over 2. And I don't know what that is. To the nearest square centimeter. 140.4 centimeters squared. Okay, if we want to know the lateral area, we would just do 3 of these. So it's going to be 3 times 9 times 7.8 over 2. And that is 105.3 square centimeters. Okay. All right. Questions with that so far? All right, cool. So now we're looking at a right square pyramid. Okay, right square pyramid has base dimensions 8 feet by 8 feet and a height of 16 feet. Calculate the surface area of the pyramid to the nearest square foot. Okay, so let's start out maybe by drawing in some of these values that we know. The base is 8 feet by 8 feet. So this is 8 feet, and this is 8 feet. And the height is 16 feet. Well, which height are we referring to here? Yeah. The height in the middle. This is 16 feet. Okay, now to get the surface area of this thing, we need to know the surface area of the base. Well, that's fairly straightforward. It's 8 times 8. And we also need to know 4 of the triangles. In order to get the triangles, we actually need to know the slant height, not the height. So we need to take an additional step to try and figure that out. Now what I'm going to do is I'm going to draw a line along the base that connects this point to this point. And this will be a right angle. Okay. How long is this part over here? Actually, let me just redraw it outside. I'm going to redraw it outside of the pyramid so we can get a better idea. This is 16 feet. How much is this along here? It's 4, right? It's half the base. Exactly. Now we want to know this. So what can we use to figure it out? Yeah, I'm hearing some of you say it, right? Pythagorean Theorem. A squared plus b squared. I'm hearing some people say c squared. That's fine. Usually equals c squared. People write it that way. I also like writing it as h squared. Why do you think I would use the letter h there? Yeah, it's the hypotenuse. Yeah, and the hypotenuse must be the square that's isolated. Really important when you're using the Pythagorean theorem that the one that's by itself is the longest side. Okay, so here what we're trying to find is the longest side, so that's s squared. And the other two, it doesn't really matter. Okay, so if we add up 4 squared plus 16 squared on a calculator, that is 272 equals s squared. So how are we going to get s? Square root it. And that works out to be 16.4924. I'm going to keep 4 decimal places. Okay. Now this is just an important thing to note, and some of you guys, if you've done some science this year, may have learned about significant figures. Do anyone know what I'm talking about? Okay, couple. So if you haven't taken science yet, you will learn about it next semester. Basically, the idea is that when you are rounding in a problem, here we want to round to the nearest foot. If you're doing an intermediate step, keep extra decimal places. Okay? If I were to round this here to the nearest foot, that would round to 16. And that's quite a bit off from 16.4924. Okay? So you want to keep extra and only round in the very final step. And it has to do with the fact that every time you round, you get a little bit further from the exact measurement. And so if you round multiple times within one problem, you're going to end up being quite far away from the actual value. Okay, all right, so now we can figure out the surface area of this pyramid, because the surface area is the square plus 4 triangles. And we now know the height of the triangle to be 16.4924. Okay, so for the square, we're looking at 8 times 8. And the 4 triangles, we're looking at 4 times, base is still 8. The height is that slant height, 16.4924 over 2. Okay, and that is, I don't know. I don't know what that is. What is it? Well, this is 64. 8 times 8 is 64. Lots of emails coming in today. This is 263.8784. So all together, if I add 64 to that, now this is my last step, so here I can round to the nearest square foot. Okay, so this is, it's 327.8784, but I'm just going to write 328 square feet. Okay? Now, just as an FYI, I could actually give you this problem and say, tell me the surface area to the nearest square inch or square meter, which is just adding in an extra layer because we're bringing in what we did on Friday, where now you're actually also including a unit conversion in there as well. Okay? All right, so I'm going to get you guys to try these two, and then we'll start to talk about cones. All right, so we're going to talk now about cones. And I got to tell you that for cones and spheres, the proof for some of these formulas is a little bit involved. Some of them are more involved than others. Just give me a sec. I'm going to pause this. All right, so for cones and for spheres, the formula for things like surface area and volume are a little involved, okay? So, and it's not a requirement of this course. For the sphere piece, I actually cannot derive it for you yet because you need some calculus knowledge to be able to do so. So I'm going to give you those formulas. And for the cones, I could actually derive surface area, and I could derive the volume of cones and pyramids for you. But I've spent quite a bit of class time in the past doing this, and some people just love it, and then a lot of people are like, this is so confusing and I don't need to know this, okay? At the same time, I really don't enjoy like just giving you a formula and letting it drop from the sky and say just use it. So what I'm gonna do is I'm gonna create a video and put it on, I'll link to it on D2L, around how these formulas are derived. Okay, so I'm just going to tell you what it is for now. If you want to watch it, please, by all means, go ahead. I can give you a full proof for the surface area of a cone. I can give you a full proof for the volume of a pyramid. The circle stuff is a little bit, you need to have a little bit more math knowledge to be able to figure that out. But I can give you sort of a partial proof, okay? But let's just talk about a cone for now. Today we're just going to talk about what are the formulas and how do we use them. A cone, and I've just kind of made one out of paper, usually has two faces to it. This one is empty because I just made it out of paper, but it's got this base that's a circle, and then there's like the cone part. Okay, so there's two faces. One of them's a circle. You can see in the formula, part of this is pi r squared, so that's the circular face. And then the other face is actually, if I unravel this, part of a circle. This is called a sector. It's like a piece of pie, okay? And the formula for this is pi rs, where s is the slant height of the cone. And in fact, when I unravel this, you can actually see s becomes the radius of this larger circle as well. And that's going to be important in that proof, okay? For today, though, let's just write out the two different parts. There's this guy and this guy. And the surface area of this part, it kind of looks like a fan, is pi rs. And of course, the area rather of a circle is pi r squared. Okay? If you're just looking at the lateral area, then you would take out the pi r squared piece because you would take out the base. All right? Okay. Let's look at some examples. A right cone has a base radius of 2 feet and a height of 7 feet. Calculate the surface area of this cone to the nearest square foot. Okay, so surface area of the whole cone is going to be pi rs plus pi r squared. But we don't know s yet. It's going to be the same situation as when we were looking at the pyramids. We have to use Pythagorean Theorem to be able to figure out the slant height. Okay, so we have to do that first. So we're going to have 2 squared plus 7 squared equals s squared. And this is 4 plus 49, so that's 53 equals s squared. So s equals the square root of 53. And that should be 7 point something. 7.280. Okay, thanks. Okay, and that's feet. So now I can just take this and pop it into the s variable, and then the radius, of course, is 2. So the surface area is pi times 2 times s, which is 7.280, plus pi times 2 squared. Okay, and you can just do that all on a calculator all at one time if you wish. Okay, so pi times 2 times 7.280 plus pi r squared. Okay. All right, I'm getting to the nearest square foot. I get 58. Okay. Now, I would like to see this line where you substitute when you're showing your work. Because then if you show me this, but you make a calculation error, you're probably going to get full marks. Okay, so please make sure to do that kind of thing. I'm going to let you guys try this one, and then we'll finish off talking about spheres today, and then we're going to finish up the rest of surface area tomorrow. All right, so we're going to finish off today talking about spheres, which is a ball shape. Formula for the surface area of a sphere is 4 pi r squared. This is another one where I will make a video with like a partial proof for the surface area of a sphere, but if you want to really know why, then you have to keep going a little bit until you get into about, I think it's like the second semester-ish of calculus in university. It's been a long time though, so I can't remember exactly. Okay, surface area of a sphere is 4 pi r squared. So for example, the diameter of a baseball is approximately 3 inches. Determine the surface area of the baseball to the nearest square inch. Okay, so really the only thing we have to be aware here is that we're given diameter is 3 inches, and we need to know the radius to calculate the surface area. Yep. Right, radius is 1.5 inches. Okay, so the surface area will be pi times 1.5 squared. And that is, I don't know, 28.27 to the nearest 8-inch, it's just 28 square inches. Okay, so that's a sphere. This guy is on your formula sheet. What is not on your formula sheet is what we're about to look at, which is a hemisphere, which is half a sphere. Okay, so there's two kinds of hemispheres. One of them is a solid hemisphere, and one of them is a hollow hemisphere. Okay, so if you think of a solid hemisphere, that's like if I took an orange and cut it in half, it's solid in the middle. So I would be looking at that would be a solid one. A hollow one would be like if I ate the inside of the orange and then cut it in half, if that's possible, and just looked at the peel. Okay. Now, a question I often get about the hollow hemisphere is, do you count the area of the outside and the inside? And it's a good question, and it often causes some ambiguity because in certain circumstances, I can see why you'd want to count the inside as well, right? If you're looking at, like, you make a hemispherical bowl out of pottery, let's say, and you're glazing it, you would want to glaze the inside and the outside, right? For the purpose of this course, we're going to assume that a hollow hemisphere is just the outside, okay? So it's almost like, imagine I asked you for the surface area of the northern hemisphere of the Earth. You would just be looking at half, okay? So assume for hollow in this course that we are not also considering the inside of the bowl-like shape. Okay, so for a solid hemisphere, there's actually going to be two surfaces. One of them is the hemispherical surface, the circle, and then there's also going to be the circle on the inside because it's not hollow, it's a solid circle. Okay, so to get the whole surface area, we have to take half of a sphere. Well, half of a sphere, instead of 4 pi r squared, is going to be 2 pi r squared. And then we have to add the circular base, which is pi r squared. Okay, now some people just write this as 3 pi r squared. You can absolutely do that. Personally, I like to split it up because I like to be able to see each surface within the formula. But if you want to write it as 3 pi r squared, that's totally fine. If you're looking at a hollow hemisphere, that would just be half a sphere. That's 2 pi r squared. Yep.
Are we going to get a lot of questions with this?
You could, yeah. This is not on your formula sheet, so you need to be able to work with the formula for a sphere and figure out how you would solve this type of problem. Okay? All right, now a hemispherical bowl has a radius of 8 centimeters. What is the surface area of the hemisphere if it has a lid to the nearest square centimeter? And then what's the surface area of the hemisphere if it has no lid to the nearest square centimeter? Okay? In the first case, we're talking about a solid hemisphere because the lid itself is a surface. Okay, so this is going to be the first one that we looked at. Surface area equals 2 pi r squared, and r in this case is 8.0, plus pi r squared, pi times 8.0 squared. And I don't know what that is. Let's see. Uh, 603. What does it say? To the nearest square. So 603 centimeters squared. And then for just the hemispherical bowl with no lid, that would be 2 pi times 8.0 squared, which is, let's see, 402. Okay. If you're worried about the question being ambiguous around a sphere, you can just ask and I'll clarify. Okay, but just remember for this course, when we're looking at a hollow hemisphere, we're just considering the outside of the shape. Okay? Any questions so far? All right, so we do still have some stuff to talk about with surface area. We're going to continue that tomorrow. Mainly what we're going to talk about are two things. Number one, how do I figure out the surface area of a composite shape? Meaning I'm taking two shapes like these two and putting them together, because then some surfaces get covered up. That's one piece. And then the second piece is we're going to talk about what if you have to work backwards? What if you know the surface area of a cylinder, let's say, and you know the height and you're trying to figure out the radius? How do you solve that kind of problem? Okay, so I'm going to stop here for today and we will pick that up on Tuesday, tomorrow.